In the last video, we saw that the division algorithm in Z led to a Euclidean algorithm, which allowed us to compute the GCD of two integers. So I want to start this video by talking about that same idea in a general Euclidean domain. So let's say R is a Euclidean domain. That means it has a division algorithm. And the division algorithm in R gives a Euclidean algorithm by successive divisions. So what does that mean? Let's say that A and B are in R, and B is not 0. Then, applying the division algorithm, you can write A equals Q0 times B plus R0, where the norm of R0 is less than the norm of B. Then you can do it again and write B as equal to Q1 times R0 plus R1, where the norm of R1 is less than the norm of R0. And then you can do it again, and you get R2, and so on and so on. And eventually, you hit some point where the remainder that you get is 0. So you get Rn minus 2 equals Qn times Rn minus 1 plus Rn. Rn minus 1 equals Qn plus 1 times Rn plus 0. So how do you know? So Rn, what is that? That is this last non-zero remainder that occurs. So how do you know that a last non-zero remainder has to occur at all, that you don't just go on like this with successive divisions forever? Well, when you're applying the division algorithm, you first have the norm of B, and you know that R0 has norm less than the norm of B, or the remainder would be 0. So you have norm of B bigger than norm of R0. And then what is R1? Well, it's something where the norm of R1 is less than the norm of R0. The norm of R2 is less than the norm of R1, and so on. So every time you apply the division algorithm again, the remainder that you get has strictly smaller norm than before, or it's 0. And what are we getting? We're getting a decreasing sequence of non-negative integers. And no decreasing sequence of non-negative integers can go on forever. It has to terminate. Like if norm of B is 2, norm of R0, it's either 1 or it's 0. And then what is the norm of R1? Well, it's even less than that. And at some point, you're done. Like when you hit a 0, you can't have anything less than that. So the remainder has to be 0. OK, so you apply the division algorithm over and over again, and you write A equals Q times B plus something. B equals Q1 times, or sorry, Q0 times B plus something. B equals Q1 times R0 plus something. And it terminates after finitely many steps. And in the case of Z, we connected this to computing GCDs. And we're going to do that for a general Euclidean domain as well, that there is a nice notion of what a GCD should be. And you can compute them algorithmically using this process. So before moving on, I just want to highlight one thing, which is in the division algorithm, in a Euclidean domain, there's no guarantee that these Qi's and Rj's are unique, right? So there's some kind of question about uniqueness that we'll talk about more later. So we'll come back to this idea of the Euclidean algorithm and GCDs in a general Euclidean domain in the next lecture. So I'm going to pause and erase, and then we'll talk about examples of Euclidean domains. Now let's talk about some examples of Euclidean domains. So at the very beginning of the first video, we said that every field is a Euclidean domain. So that's our first example. If F is a field, it's a Euclidean domain. To specify a Euclidean domain, to show that something is a Euclidean domain, you have to describe a norm function on that ring that has certain properties. Well, what is the norm function that you should choose for F, a field? It's a Euclidean domain with any norm function. OK, so for example, we could pick the norm function that just says norm of A is 0 for all A and F. And why is that? So what needs to be true for F to be a Euclidean domain is we need to have a division algorithm. So we need, for every A and B in F, where B is not 0, we need there to be some Q in F so that we can write A equals Q times B plus some R, where either R is 0 or the norm of R is less than the norm of B. But because F is a field for any A and B and F with B not equal to 0, there exists a Q in F so that A equals Q times B plus 0. A equals Q times B. How do we know that that's true? Well, we can say what Q has to be. Q has to be A times B inverse, because A times B inverse times B is A times 1, which is A. So A equals A plus 0. Okay, so fields are Euclidean domains for sort of trivial reasons. So let's see our next important example. Z is a Euclidean domain with norm of A equals the absolute value of A. So what are we actually doing now? We're proving the division algorithm in Z, which we haven't done earlier in this course, but I think it's worth doing here because it sort of illustrates like how one shows that anything has a division algorithm. So it's a useful thing to see, even if you've seen it before. Okay, so let's take A and B and Z and B not equal to 0. And for now, let's suppose that B is bigger than 0, and we'll see what to do when B is negative. So let's go along the number line, like the real number line, and just mark off the multiples of B. So we're seeing that going from one multiple of B to the next is partitioning the real numbers. That the intervals from n times B to n plus 1B, half open intervals that include nb but not n plus 1b, partition the real numbers. That every real number is in exactly one of these intervals. So A is in exactly one of them. That means that, let's say, A is in Q times, let's say the interval from Q times B to Q plus 1 times B. So now what happens if we take A minus Q times B? Well, that's equal to something in the interval from 0 to B. Why is that? Well, just what A is somewhere in here. You subtract the bottom endpoint. So what is R? It's the distance from A to the bottom endpoint. And that's somewhere in between 0 and Q plus 1B minus QB, which is B. And that's it. So when B is positive, that's the whole proof, right? This is what we were trying to show. So the norm of R, absolute value of R, is between, it's certainly less than the absolute value of B. That's what we know here. Okay. What do you do if B is negative? Well, if B is negative, let's just apply the division algorithm to negative B. And we know now that A equals some Q times negative B plus R, and either R is 0 or the absolute value of R is less than the absolute value of negative B. But the absolute value of negative B is the absolute value of B. So that means A is equal to some integer, negative Q, times B plus R. And we know that either R is 0 or the absolute value of R is less than the absolute value of B. So when B is negative, you get the statement from the statement for B positive for free with the observation that B and negative B have the same absolute value. And something I just want to point out, which is something that I said at the beginning of this video on the sort of first board, is that Q and R here are not unique. That there are some questions about like when the division algorithm is giving you some kind of uniqueness. Here you are not getting uniqueness. If you let A equal 5 and B equal 2, applying the division algorithm, like 5 is equal to 2 times 2 plus 1. 1 is some integer, and the norm of 1 is less than the norm of 2. Absolute value of 1 is less than the absolute value of 2. So this is the kind of representation that the division algorithm is promising us. But you could also say that 5 is equal to 3 times 2 plus negative 1. Negative 1 is an integer, and the norm of negative 1 is less than the norm of 2. So we're getting two different representations of 5 in the form that the division algorithm promises us. So there's no uniqueness here, but you get uniqueness if you put in another assumption and you say that R has to be greater than or equal to 0. Okay, so there's just something to think about here that I want you to be aware of. All right, so I'm going to pause and erase, and then I'll come back to an example that we talked about in the first video, which is going from z to f bracket x. Our next big example comes from polynomials. Let's let f be a field. Then f bracket x is a Euclidean domain with norm given by norm of p of x is the degree of p of x. And the proof of this is a statement that comes later in Dummett and Foote. This is theorem 3 in section 9.2. So Dummett and Foote prefer to sort of hold all of the proofs of things about rings of polynomials to chapter 9, which is all about polynomial rings. But I would rather prove this one now because this is probably something that's already familiar to many of you. It's really nothing more than the idea of polynomial long division. So what do we need to prove to see that f of x, f bracket x is a Euclidean domain? We need to show that it has a division algorithm. So what do we need to see? If a of x and b of x are polynomials in f bracket x and b of x is not 0, then there are unique q of x and r of x in f bracket x with a of x equals q of x times b of x plus r of x, where either r of x is 0 or the degree of r is less than the degree of b. Okay, so this uniqueness is a little bit more than what we need to show that f bracket x is a Euclidean domain. But since it's true, we might as well prove it now. So we're going to prove that there exist q and r with this property. And then we'll prove that they're unique after that. So let's do existence first. If a of x is 0, then we can take q of x equals r of x equals 0. And this certainly is true. 0 equals 0 times b plus 0. And r of x is 0, so we're good. So there's nothing to do. So let's assume that a of x is not 0. And once it's not 0, it's a non-zero polynomial. It has some well-defined degree. So let's name the degree of a of x, call that n. And the degree of b of x, we'll call that m. So b of x we know is not 0 by assumption. And the idea here is going to be induction on n, the degree of a. So first, there's only one interesting case for the ordering of these degrees. If n is less than m, that is the degree of a is less than the degree of b, then we can solve this. We can see that this is true sort of for free. Just take q of x to be equal to 0 and r of x equals a of x. So we've written a of x equals 0 times b of x plus a of x. And what do we need? We need that the degree of a of x is less than the degree of b of x. And that's true if n is less than m. So there's nothing to do. So the interesting case is when n, the degree of a, is at least the degree of b. And let me point out, if both of these are degree 0, that means that there are polynomials of degree 0 in a field. Neither one is 0. So they're constants. They're elements of this field. And we just saw before when we were discussing the fact that every field is a Euclidean domain, we can just write a equals q times b plus 0. So in this case, there's nothing to do. OK, so a is a polynomial of degree n, b is a polynomial of degree m. That means we can write them out. A n x to the n plus a n minus 1 x to the n minus 1 plus a1 x plus a0. And the fact that the degree is n, that means that a n is not 0. B of x is bm x to the m plus b1 x plus b0. And again, the degree of b of x being m means that bm, this coefficient, is not 0. And what we're going to do is define a polynomial a prime of x, which will be a of x minus am over bm, or if you like, am times bm inverse, times x to the n minus m times b of x. So let me just note, I want to be consistent with the notation in Dummett and Foote. This prime is not at all having anything to do with the derivative. It's just what they call this polynomial. OK, what do we see? We'll see, we do see that the degree of a prime of x is less than the degree of a of x. Because here, the leading term is an x to the n. And what's a leading term over here? Well, you take x to the n minus m times b of x. You multiply the whole thing by all of b of x by x to the n minus m. And now the leading term is bm x to the n. Everything else has degree less than n, all the other terms. And now you multiply by am over bm, and you get the leading term of this is an x to the n. So what have we done? We've chosen exactly the right monomial, exactly the right thing, like a single term to multiply b of x by, to cancel off the leading term of a of x. So that's the idea of polynomial long division. So the leading term here is an x to the n. The leading term here is an x to the n. You subtract, and I don't know what you have left over, but you certainly have no term of degree n or higher. So the degree of what's left is less than n. Okay, also let me just note, this is a thing that you're allowed to do. am over bm makes sense because bm is not 0. So bm is an element in a field. It has an inverse. Yeah, so that's sort of all I want to say here. And now, okay, so what are we going to do with this a prime of x? Well, we said the big idea here is induction on n. And now this is a polynomial in f bracket x that has degree less than n. So by induction, we can apply the division algorithm to it. So I'm going to pause and erase, and then we'll see the details of the rest of the argument. So we've defined this polynomial a prime of x as a of x minus am over bm times x to the n minus m times b of x. And we've seen that its degree is less than n, the degree of a of x. So now we're going to apply the induction hypothesis to this, which is a prime of x equals some polynomial q prime of x times b of x plus r of x, where either r of x is 0 or the degree of r is less than the degree of b. And now here's the idea. We're going to define q of x to be this q prime of x that comes from the induction hypothesis plus am over bm times x to the n minus m. Why are we going to do it that way? Because what happens now when we multiply q of x by b of x? We get q prime x times b of x, which shows up here. That's almost a prime of x. It's a prime of x minus r of x. And then, okay, what else when we take q of x times b of x? We get am over bm times x to the n minus m times b of x. And what is that? Well, that is the difference between a of x minus a prime, or sorry, it's a of x minus a prime of x. So if you take a of x and you subtract q of x, b of x, what are you left with? Just this r of x from before, from applying the induction hypothesis. So this is the same r of x as before. So r of x equals 0, or the degree of r is less than the degree of b. And this completes the proof of the induction step. So what's the idea? You choose the right thing to multiply, the right monomial to multiply b of x by, to cancel off the leading term of a of x. You apply the induction hypothesis to the thing that is left over, and that gives you a good choice for what the quotient should be when you divide a of x by b of x. So you can verify that all of the steps here work. If you were trying to come up with this argument yourself, I think the thing to do would be to actually try to prove this, starting from, okay, polynomials of degree 0, nothing really to do. Polynomials of degree 1, sort of straightforward to do. You'll see how to do it. And then if you try to prove this for polynomials of degree a little bit larger, you'll see that you'll end up using the statement for the case of polynomials a degree lower. So if you were going to try to prove this by hand, I think that would be the way to approach it. And it would bring you to this kind of induction idea. And here we're just doing it all at once. Okay, so that proves that there exist polynomials q of x and r of x with the properties that we need for the division algorithm. But we haven't yet proved the uniqueness piece. So let's do that now. So let's suppose that A of x also equals q1 of x times b of x plus r1 of x, where these polynomials q1 and r1 satisfy the things that you need in the division algorithm, that either r1 of x is 0 or the degree of r1 is less than the degree of b. So now we have two different good ways of writing a of x as something times b of x plus a remainder. So let's subtract off both those somethings times b of x. So we get these two polynomials, a of x minus q of x b of x, and a of x minus q1 of x b of x. And what do we know? This first one equals r of x. This second one equals r1 of x. Both have degree less than m, the degree of b, or 0. So the important thing here is these both have degree less than m. So let's subtract these two polynomials. These are two polynomials of degree less than m. When we subtract them, we get another polynomial of degree less than m, or maybe it's 0. And what is the difference? Well, this minus this, you end up adding the q1 of x times b of x, the a of x cancel. You get q1 of x times b of x minus q of x times b of x. You can use the distributive property to write this as q1 of x minus q of x times b of x. And you know that this is a polynomial of degree less than the degree of b. And this is a problem because the degree of b, like if you take b of x and you multiply it by something, you're getting a polynomial. Because degrees of polynomials add, the degree of this should be at least the degree of b, or this product is 0. So because we know that this product has degree less than the degree of b of x, this must be 0. And OK, f bracket x is an integral domain. B of x is not 0. That means that q1 of x minus q of x must be equal to 0, which means q1 is equal to q. And once you see that q1 is equal to q, now you subtract, you see that r is equal to a of x minus q of x b of x, and a of x minus q1 of x times b of x is the same as a of x equals minus q of x b of x, because q equals q1. So we see that r equals r1 as well. So that completes the proof of uniqueness here.